We're now going to look at the study of the properties of logarithms. I'd like to read something again, kind of out of the book for you. The ability to manipulate logarithmic expressions is important in many applications, and especially in advanced mathematics. In this section, we're going to learn about the properties of logarithms, of which we've already discovered 2 of those properties. There are 6 that I'm going to share with you. Again, I'm going to talk about the first 2 that we've already learned about, but what I'd like to point out to you is if you would remember in Course Compass to click on the Assignments button, and then towards the bottom of the 5 or 6 items there, you'll see a category titled Supplemental Material, or it might say Important Material from your instructor. Click on that and look for the appropriate chapter. Click on your chapter, and then look for the properties of logarithm file that I've put there for you. It gives you the 6 properties that we're going to speak about right now. The first property we've already mentioned in the past, and that is the logarithm of 1 is always equal to 0. It does not matter what the base is. The base can be 10, the base can be 5, the base can be 100. It doesn't matter, because any number, let's call it a b here, any number raised to the 0 power is always equal to 1. That's why the log of 1 is equal to 0. The second property that we've already discovered is that the log of a, where the base is a, is always equal to 1. And that's because when I put this in exponential form, I'll take the base of a, raise it to the first power, and that's always going to be equal to a. So these are 2 very important properties. Log of 1 is 0. The log of a, where the base is the same, and the bottom line is these 2 match, is always equal to 1. The next property that I'd like to introduce is the logarithm of the product of 2 numbers, where the base is a, is going to be equal to the log of the first plus the log of the second. I'm speaking of the products here. The log of the first product plus the log of the second product, where the base is the same. And the reason for this, and I'm going to go back and prove this one to you. I'm not going to prove any others after that, but again, I want you to see that. The reason for this is logarithms, because by definition they are an exponent, they behave like exponents. And so, with exponents, when I multiply, I add those exponents, and I get x to the 5th. And so with logarithms, when I multiply, I add the log of those separate products. I'm going to come back to this in a minute here and look at a proof of this property. Okay, all I would like to do now is to prove the property that we just spoke about. The logarithm of the product of 2 or more numbers is equal to the sum of the log of each of those products individually. I'm only doing this because I'm only doing the proof, because I'd like you to feel and understand these properties. I'm not going to ask you to do any proofs on your test, but I want you to be comfortable with using these manipulations because you're going to use them so much in the end of this chapter. So what I've decided to do then is I'm going to let this expression right here, the log of m where the base is a, I'm going to let that equal u. And I'm going to let the log of n, where the base is a, equal v. So that's a premise. I'm starting out with that. And then what I'm going to do is I'm going to take each one of these expressions and put them in exponential form. Remember, a logarithm is an exponent. So this is my exponent. So I have the base of a to the u power is equal to m. And here I have the base of a to the v power is equal to n. And now what I'm going to do, because I'm talking about the product rule, I'm going to multiply m times n together. Well, that means taking a to the u times a to the v, because this is m and this is n. Well, I know that by my property for exponents, if the bases are alike, that I should add those exponents, u plus v. And now I'm going to put this back into logarithmic form. So remember, a logarithm is an exponent, so this is going to go all alone. So I'll have u plus v equals the log of m times n, where the base is a. I'm almost done now. And finally, this right here is this statement right here. I'm going to come back to my original premise, and I'm going to replace the u plus v with this for u and this for v. And I'm running out of space here. I guess I'm going to come out over here and do that. U again is the log of m, where the base is a. And v is the log of n, where the base is a. And all of that is equal to this log of m times n, where the base is a. So we've just proven this property. What we're going to do next is we're going to go ahead and use this a little bit. And I think I'll just continue on without stopping the camera. Let's take a look at a problem that we might encounter. And it looks like this. If I asked you to take the log of 21 times 4, where the base is 3, and I asked you to express this as the sum of logarithms. So again, this reads 21 times 4. All I'm asking you to do is to write this as the log of 21 plus the log of 4, where the base is 3 in each case, and I'm done. You've written the log of the product as the sum of logarithms using this property. Another example, the log of xy, where the base is a, I would write that as the log of x plus the log of y, where the base is a, for each. All right? And finally, another example, the log of 3 times z, where the base might be a 2, is going to be equal to the log of 3 plus the log of z, where the base is 2, and I have expressed these as the sum of logarithms, given that we were taking the logarithms of a product. I need to be able to use this property. I need to be able to go from one to the other. Using this multiplicative property, you might be asked to go in the other direction. For example, you might be asked to express several terms as a single logarithm. So what I've got here to have you work with is the log of 5 plus the log of 11, where the base is 4 in each case. So I'm going to go from this direction over to here. So I'm going to write this as the product of, the log of the product of those two values, the 5 times the 11, where the base is 4. And 5 times 11 is 55, and I'm all done. I've written the sum of two logs as the log of a single log. Another example might be if I asked you to take the log of z, where the base is b, plus the log of 2, where the base is b, and to write it as a single logarithm, you would just tell me that that's the log of 2 times z. I'll write that as a monomial. Where the base is b, I always put the coefficient of 2 in front. That's it. I've gone in the other direction. Here's our next property. It says that if I want to take the log of a number raised to a power, given some base, that can be reduced to, this exponent right here, can be brought down in front and called k times the log of that value m, where the base is a. This can be very, very useful in solving logarithmic and exponential equations. So this property needs to be, all these properties need to be retained. You need to make a note card of them, memorize them. Now mind you, this isn't a proctored test, so you would have that note card, of course, available to yourself. But get comfortable with that, especially if you're going to take the next class. Some examples of this, if I had the log of x to the 5th, where the base is 2, whenever I see this, really, all I'm asking you to do is to take this 5 and bring it down in front. And I'll be doing that symbol quite often. So I can write this as the product of 5 times the log of x, where the base is 2. And I'm all done with that problem. Another example, I might ask you to take the log of m raised to the negative 6th power, where the base is c, and rewrite that using this property. So I'll have a negative 6 times the log of m, where the base is c, and I'm done. I've used this property successfully, and I should be able to go backwards as well. An example of that would be if I had 3 times the log of x, where the base is 2. You need to recognize that you might need to write that as the log of x cubed. So bring the 3 on up front, where the base is 2, and you've used this property in reverse. Well, now we're at the quotient property of logarithms, and like the multiplicative property, where we've said the logarithm of the product of two or more things is the sum of the logarithms of those various products, I would do the same thing with quotients. Remember, with exponents, when you divide, where the bases are alike, you subtract. So when I divide the logarithm of a quotient, I would write it as the difference of the logarithm of the numerator minus the logarithm of the denominator. So, for example, if I had the log of 3 divided by 7, where the base is 2, and I asked you to write this as the difference of logarithms, then all you would do for me is you would tell me that that's the log of 3 minus the log of 7, and I always put this base in after the fact because then I don't forget it. I'll put in this common base of 2. I'm done. I've written this as the difference of logarithms. If I were to ask you to take the log of p divided by r, where the base is 5, and write it as the difference, you would write this as the log of the log of p, I don't know where I got that 5 from, minus the log of r, oh yes, the base of 5, where the base is 5. And I'm done. I've written it as the difference. And now in the other direction, if I asked you to take these two terms and express them as a single logarithm, when you see that minus sign, you need to think division. And so I would write this as a single logarithm by writing this as the log of 15 divided by 3, where the base is 8. And since that divides evenly, you should go ahead and say that that's equal to the log of 5, where the base is 3. And you're all done with that problem. I might give you another problem that says take the log of 5 divided by x, where the base is b. Actually, I'm going to change that. It's not doing what I'm wanting to do here. The log of 5 minus the log of x, where the base is b. And again, I asked you to write this as a single logarithm. You would say to me that that's the log of 5 divided by x, because I have a difference here where the base is b, and I can't simplify, so I'll leave that one alone. And next we'll ask you to use the properties together. Put the multiplication property, the division property, the property where you have an exponent on the log of the number. Put those together and write these as the sum, difference, or product of several terms. So when I give you a problem like this, the log of 12 times x squared times y cubed, you need to think multiplication, and multiplication means to add. And so I can write this as the sum of the log of 12 plus the log of x squared plus the log of y cubed. And I'll go back in and put my base now. My base is an a for every one of these. I do that at the end so I don't have to think about it. And I could see I'm done. If the directions said right is the sum of logarithms, you are done. However, I'd like you to remember the property that when you have the log of something raised to a power, that you can bring that exponent down in front. It's true for this as well. And so another step might be to keep the log of 12, where the base is a, but to bring this 2 down in front, so I'll have 2 times the log of x, where the base is a, plus 3 times the log of y, where the base is a. So again, notice that I brought the 2 down in front and the 3 down in front. And for that matter, if I wanted to, and these problems could go on and on and on and on. And this is going to be a handwritten test, so I'm going to be able to look at your work and judge that you were able to do a step and maybe another step. But if a person wanted to, they could think of 12 as 3 times 4, or heck, 2 times 6, or 1 times 12, you know, all those options. And so if you thought of 12 as 3 times 4, you might even consider writing this problem as the log of 3 plus the log of 4. That represents the log of 12, and then bring down the rest, 2 times the log of x, and 3 times the log of y. And let's see, I got my bases in place. I'm all set. That's another correct answer. So what I want you to know is that as you do your work, there might be times when your answer might not match the book's answer because you took it another step, or they didn't, etc. But what we're trying to do now is apply all the properties to logarithms and write them as a sum, difference, or products. This problem is going to involve the quotient rule and the rule where we have an exponent on the number that we're taking the log of. So involving the quotient rule makes me think subtraction. So I'm going to first, now you could do this all at once if you wanted to. I'm going to first leave the p cubed and the q to the 7th together. And then I'm just going to write this as the difference of the log of m to the 5th. So all I did is use the quotient rule at this point because I had this division symbol. But next I'm noticing that I have the product here of p cubed times x to the 7th. So I might write that as the sum of two terms. The first one being the log of p cubed, and the next one being the log of q to the 7th. So I've broken that down. Again, where the base is b for each of those. And then I'll bring down my log of m to the 5th where the base is b. And I would consider, personally, bringing these exponents down in front now. It is a really good habit to get into because this is what you're going to have to do when you solve equations, logarithmic equations. And so I'll have 3 times the log of p, where the base is b, plus 7 times the log of q, where the base is b, minus 5 times the log of m, where the base is b. And finally, I can think of nothing else that I can do to write this as the sum, difference, or product of terms. Again, I want to use all the properties to write this as a sum, difference, multiple of logarithms, and I see a radical symbol here, but underneath that radical is an expression that can be simplified. You have a to the 6th over a to the 2nd, that's equal to a to the 4th because we subtract the exponents. B to the 8th over b to the 5th is equal to b to the 3rd because we subtract the exponents. So let's do that first. So let's write this as the log of a to the 4th, b to the 3rd, where the base is b. Now, the convenient way to deal with this problem now is to think of this radical as everything, the radicand raised to the 1/2 power, as we have done with radicals before. Because I'm taking the square root of all this, I could write this as the log of a to the 4 over 2 power and b to the 3 over 2 power, where the base is b. And I should simplify that and call that a squared and b to the 3/2, but that's all I'm going to do. And now I see, I've gotten rid of my radical, I see that I have the logarithm of the product of two things. So I'm going to write it as the sum of, so I'll have the log of a to the 2nd power plus the log of b to the 3/2 power, where each of them had the base of b. And now what I'm going to do is I'm going to bring my exponents down in front, so I'll bring this one down here and this exponent down here. So I'll have 2 times the log of a, where the base is b, plus 3/2 times the log of b, where the base is b. And all I want you to notice right now is this right here will sneak up on you relatively regularly. We said that the logarithm of a number where the base is exactly the same is equal to 1. So 1 times 3/2 is 3/2. So my last term in this problem will be just 3/2, and I'll have 2 times the log of a, where the base is b, plus that 3/2. And I have simplified that expression. Pretty interesting that I've gone from this all the way down to that, and that I was able to get a term that is just a rational number. Unlike the last couple of problems, now what I'm doing is I'm expressing the difference of two terms as a single logarithm. So that's what the directions would say to you, is express this as a single logarithm. So a couple things you've got to be on the lookout. This right here can be moved way up here, and that's the only way. I cannot choose to put this back into a division problem until I get rid of this factor of 2 and move it up here. So what I'm getting at is that right there has got to become the log of the square root of x raised to the 2nd power. You got to get that up and away. And then this one, the x squared, that 2 is already up there. It's okay. Now the square root of x squared means the square root of x times the square root of x, which is just x. So what I've got there is the log of x, and then here I've got the log of x squared. Now, having simplified that already, or to this point, now I'm ready to write this as a quotient. So I could write this as a single term, x squared divided by x, where the base is a. And finally, that reduces right there. The exponents subtract, and that reduces to x. And I've taken this expression and written it as a single term. This problem is ready to be written as a quotient because I have nothing in front of logs of each of these two terms. I have a different sign here. So I can write this as the logarithm of a single term. In the numerator, x squared minus 4, and in the denominator, x minus 2. where the base is a. But now I ask you to think of your work with rational expressions and to remember that if you can, simplify this. And so this numerator can be factored. I'm just going to come over here and factor that out to the side into x plus 2 times x minus 2. And the denominator down there is already in prime form. It is equal to x minus 2. So that fraction there that I'm taking the log of can be reduced. The top and the bottom have a factor of x minus 2 that can be removed out of that. So what this becomes is the log of x plus 2. I'm going to keep that in parentheses where the base is a because I'm taking the log of that whole expression. And I've simplified this into a single term. This is an interesting problem where I would wish or hope to use my calculator, just find the log of 1/3, because that's all I want you to do here, is find the log of 1/3. But I don't tell you what the base is. The base is the letter b. So, if I'm going to use my calculator, I have to know if the base is 10. And that's all I know how to do at this point, is when the base is 10. But what happens in this problem is I'm giving you some information. I'm giving you that the log of 3, where the base is this unknown b, is equal to 1.099. And the log of 5, where the base is also b, is equal to 1.609. And I'm asking you to use that and some of the properties that you know to find the result of this without a calculator. So what I have to do is I have to say, oh, hey, this is the quotient. So maybe it would be helpful to write this as the difference of two logarithms. So I would write this as the log of 1 minus the log of 3. And the reason I did that is I knew that if I could get that log of 3 alone, I have a value for that. I can substitute in. As a matter of fact, the log of 3 where the base is b, this right here, is equal to 1.099. So I didn't have to use a calculator, I was able to substitute something in. This right here, the log of 1, you need to remember that the log of 1 is always equal to 0. You got to memorize that property. And what I have here is 0 minus 1.099, so I get an answer of a negative 1.099. And I found out what the log of 1/3 is, where the base is b, and I didn't even know what the base was. But I was able to use the properties to do that. Another example, and I'm not going to stop the camera. Another example, kind of interesting. Find the log of 15b, where the base is b, and I see here a product. So I'm going to think of this as the log of 15 plus the log of b, where the base is b. Now I knew this was going to be helpful right here, because whenever I have the log of something where the base is the same, I know that I always have 1. That's another property you need to remember. So that right there is just equal to 1, and I'm trying to find the value of this whole expression. Well, I have now the log of 15. I was only given the log of 3 and the log of 5, so it looks as though I better think of 15 as 5 times 3. So I'd better write that as the log of 5 plus the log of 3, where the base is b. And those two things were given to me. The log of 5 is 1.609. I'll substitute. The log of 3, where the base is b, is 1.099. Then I add this 1, the log of b, where the base is b, and all of that adds up to be 3.708. And I was able to find the log of 15b, given this, and some properties. The last property that I'd like to remind you of, or actually share with you, we haven't talked about it at all yet, is that if I take the log of some number that's raised to a power, where the base is the same as, if you will, that base, this base raised to the 7th power, then what I'm going to think about doing is I'm going to think about bringing this 7 down in front. We've used that property a lot. And I'll have 7 times the log of x, where the base is x. Well, I've discovered that the log of x, where the base is x, is always equal to 1. Please remember that's true because x has to be raised to the 1st power in order to get x. I'm just talking about that little piece right there, if I put it in exponential form. This is equal to 1, and I have 1 times 7, or I get a result of 7. And this leads me to one of the last properties, and that is that if I have the log of a number raised to a power, and that number represents my base, that I will always get n, my exponent. So the log of x to the 7th, where this base matches this, will give me the 7. If I had, one more example, if I had the log of a squared, where the base is a, I could automatically, because of this property, just say that that's equal to 2. That concludes this section, Properties of Logarithms, and it's a very, very important section because without it we can't solve equations, and that's where we're going to be heading in one of the last sections in this chapter. You need to be very comfortable with the properties. You need to remember that the log of 1 is always 0. You need to remember that the log of a number where the base is the same is always equal to 1, that products means to add, that quotients means to subtract, etc. So practice those properties, just manipulating and using those so that you can go on to solve equations.